I should put on some headphones. That's only... How many, I wonder, ideas in physics, in modern physics and astronomy, were sort of planted in our brains through comic books?
I mean, this is definitely, not just comic books, but science fiction in general.
Yeah.
Like, let's talk about the all the conversation about our transporters becoming real, right? And would people even have been going around trying to figure out how to do something like a transporter were it not for Star Trek?
Well, we've already, when you think about the cell phone, like we've already gone past what Star Trek was telling us we should be expecting. Okay, we're live, by the way. Hey, everybody, welcome to the pre-show, the Weekly Space Hangout. Well, I'm gonna actually save the announcement for the show. I'm gonna say hello. Say hello to me in the chat, and then I'll say hello back.
Can I say hello with my voice, and you say hello back, or does it have to be in the chat?
Huh? I don't know. I've never run across this problem before, but we can do.
You're not going to say
hello?
hello?
With your voice. I'll say hello to you. Well, we're going to say hello in the show, so we don't need to say hello twice.
I thought we were friends.
We're close. All right, there we go. Everyone's saying hello. Hello to Fifth Dimension, Beth Johnson, Bob Moeller, Corvair Wind, David Dunn, Horizon Brave, John Suffield, Johnny J, Johnny Zed, Larry King, Nancy Graziano, Rich Wilson, Sir Goosey, Tom Van Scotter, and Zap Van Zappan. Hey, everybody. So how, I want to talk about the helicopter, but that's in the show too. I'm too stoked to talk about that, about the helicopter.
Let's geek out about the helicopter.
Yeah, but twice? All the zingers will be over.
I'm going to geek out about it probably about 50 times in the next week, so twice is nothing.
Yeah. Are you writing about it?
I don't think I'm writing a formal article about it. I'm probably going to take over our Twitter account for a day.
Yeah.
And gush about it.
And place your bets?
I think it'll work.
Yeah, how many flights is the question.
Oh. 2.
2?
I'm going with 2.
Yeah.
Is this the Perseverance helicopter?
Yeah, Ingenuity.
Yeah.
Yeah, I'm going to go with 5.
5?
5?
Yeah.
I'm optimistic.
Yeah. I don't know how many. I'm at exactly the right age to have bought my children just a series of drone toys. And so I can confidently tell you 1. Yeah. No, Corey S is saying Ingenuity will fly until it runs out of battery power.
If it can take off, land, and then take off again, I will be happy.
Mm-hmm. Yeah, absolutely.
I don't care if it lands a second time, really. I just want it to demonstrate that it can land and take off again.
Yeah.
And have that proof of concept. Now I'm already gushing about Ginny. Sorry.
See? Yeah. No, it's hard not to. I'm sure.
Carolyn.
I guarantee. Yeah. No, half of the show is just going to be us just nerding out about this helicopter. So.
Yes, probably.
There you go. Nancy's calling it 4 flights. All right.
4.
Yeah. All right. She's our producer, so she knows. All right. I'm going to put you guys back in the regular view, and we will start the show. There's me. Okay. Hello and welcome to the Weekly Space Hangout for Wednesday, April 7th, 2021. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about the Mars Ingenuity, of course, Lucy getting ready for flight, dark matter coming from the center of the Milky Way, and possibly more. All right, joining me this week, we've got our co-hosts. We've got, Dr. Kimberly Cartier. Kimberly.
Hey, Fraser. Happy podcast day.
Happy podcast day to you, too.
Ginny helicopter day, because we're going to gush about it for ages.
Yeah, exactly. We've got Carolyn Collins-Peterson.
Hey there, how you doing?
Good. Carolyn brought the story to us, but we are going to all just steal it from her. And we got Chris Carr. Hey, Chris.
Hello, Fraser. Happy to be here.
All right. So normally I take this moment to give a brief shout out to our good friends of the Weekly Space Hangout crew, which I will do. Go to wshcrew.space. But also I want to give a huge shout out to one of our co-hosts, Dr. Moya McTeer, who successfully passed through her doctoral defense yesterday and did it live stream style, which is pretty impressive. So if you want, you can actually watch moment by moment as she defends her doctorate from all attackers. So congratulations, Moya. We can't wait to grill you all about it. And I think our streak of continuing to mint PhDs continues. Chris, you're next. So now it could be causation, could be correlation. We can't be sure. All right. So joining us, we got a special guest this week. We've got Chanda Prescod-Weinstein. Chanda, welcome to the Weekly Space Hangout.
Yeah, thank you for having me. And I just want to shout out Dr. McTeer as well. That's pretty exciting.
Just rolls off the tongue, doesn't it?
Yeah.
So the question I always ask people, who are you? What do you do?
I'm an assistant professor of theoretical physics and core faculty in women's and gender studies at the University of New Hampshire. So that's my job title. What I actually do is spend a lot of time worrying about what dark matter is, trying to recruit students to worry about it with me, and also think about some of the social issues that get in the way of us thinking about the problem of dark matter. It's all in service of trying to figure out what dark matter is.
Now, we've talked about dark matter many times here on the show, and I was watching a presentation that you're giving about a year and I guess back in September, and you showed this Venn diagram of all of the possible solutions for what dark matter might be, and I'm sure you know the picture I'm talking about, and there must have been hundreds of possible proposed ideas for what dark matter can be. You have sort of put your stamp down in the Axion part of this. So what sort of all of the dark matter searches, you're searching for the Axion. What is it?
Yeah, so I think before we start talking about the Axion, I have to give people a little bit of a guide so that they can find the diagram that you're talking about. Oh, sure, yeah. So the Venn diagram that you're talking about, which I always tell people is the greatest Venn diagram of all time, you will not find a better one, was developed by Tim Tate, who is the chair of the physics department at UC Irvine. And so if you Google Tim Tate dark matter Venn diagram, you will probably actually find some iteration of this diagram, like just in Google image search. It's actually the ones that you'll find on Google image search are probably actually out of date at this point, because Tim made a new one for my book, The Disordered Cosmos, which just came out. I actually insisted that he update it because primordial black holes had to be added to the diagram since they're in conversation. So even though primordial black holes are kind of like the hip new thing on the street, it is the case that I think about axions, which are in the lower left-hand side of the diagram, if anybody's pulled it up and is looking around. So the axion is a hypothetical particle. We still don't know if it exists. It was developed to solve a problem in the standard model that has nothing to do with dark matter. And then it was realized soon after people realized it existed in this Pesci-Quinn model developed by Roberto Pesci and Helen Quinn, that maybe it was a good dark matter candidate. So, it's a great thing because it deals with two problems at once.
I'll take the bait. What are the two questions that it deals with at once?
Yeah, so the first problem is known as the strong CP problem in the standard model. So we have a tendency to talk about the standard model as complete, although I think today of all days, people are maybe more aware than usual that there are still questions about whether the standard model is complete. I don't know if anyone's been paying attention to the mu on G-2 announcement today, right? So there are still questions lurking around in the standard model. So in particular, the theory of the standard model predicts that the neutron will gain an electric dipole moment. So you can think of this in kind of a way that the neutron will have a funny shape that will have some distribution of charge across it. And that's like a great prediction. And it would be wonderful if we had ever seen an electric dipole moment for the neutron, but we haven't. So this is known as the strong CP problem. And Roberto Pesci and Helen Quinn came up with a mechanism to address it. And it's a beautiful mechanism. It has a particle in it. And the particle, so one of my favorite tidbits about this, it's known as the axion. I think there was a real miss here. It was almost called the Higlet. And I just think that was a missed opportunity.
I mean, is it related to the Higgs boson?
Well, the thing about particle theorists and cosmologists like myself is that we just like scalar particles. So these are particles that have no internal sense of quantum mechanical spin. Every time we're confronted with a problem, we'll see if a scalar can fix it. And back in the day, the quintessential scalar was the Higgs. And so anything that was Higgish got a name that might be, even if people are looking at the Venn diagram, you'll see that there's something called the little Higgs, and I think even the littlest Higgs on the Venn diagram. And unfortunately, they're not matched by the Higlet. I grew up reading Winnie the Pooh and a lot of A.A. Milne. Right. So I'm just going to keep harping on this. It was a missed opportunity.
Okay, so that's one problem that it solves. What's the other one?
So the other problem that it potentially solves is the dark matter problem, which is most of the matter energy content in the universe is invisible to us. So when you look up at the sky, you're seeing a lot of stuff up there. You're like, wow, that's a lot of stars. Carl Sagan swears up and down in his last book that he never said billions and billions. But the point is there are billions and billions of stars out there, galaxies. The universe is mostly what we can't see. So actually what we see is about 4 or 5% of the matter energy content. The rest is mostly dark energy. We can talk about that. I don't care about the dark energy problem because if I start to think about it, I get really stressed out. So we'll just move
the
to
fact
dark matter.
that we don't know what 90% of the matter is, and in fact we don't know what 90% of what the universe is. Yeah.
Well, look. So I'll just say quickly, right? The space-time is expanding. The universe is expanding. That expansion is accelerating. So it's hitting the gas. It's picking up speed. There's something that's causing that to happen. We have no idea what it is.
Yeah.
And this is the sort of thing that when I was in graduate school kept me up at night. So
right.
I try not to think about the dark energy problem because it keeps me up at night.
Yeah, just head down, search for the Axion. Yeah. Don't worry
so
about the expansion.
Yes.
Inevitable.
Exactly.
Sorry, I'm going to freak you out. I'll keep going.
Dark matter is the thing that I can work on consistently, be excited about, and still get between like 6.5 and 8 hours of sleep a night, which is what I need to function. So we'll stick with dark matter, which if we're just thinking about regular matter forms is about 80% of the matter in the universe. So galaxies are actually mostly made up of halos of dark matter that surround the stars and dust that we can see. So we're fairly confident it's out there, but it's invisible to us. So actually, the title dark matter is actually just a terrible.
Yeah.
It's a terrible name for it. It's not the right name.
Yeah, we've actually talked about this quite a few times here on even on this show, and the fact that, say, dark matter has all the same attributes as the neutrino. It passes through regular matter, doesn't interact. You can see through it. As you said, invisible matter makes a good name. People love the neutrino, and yet neutrinos are hot. Dark matter seems to be cold. That's one big observable difference. And yet, for some reason, people are really poo-poo. Like I'll write stories about dark matter, and people are like, I think it's just something scientists made up. Like, oh, there's so much evidence. Come on. So it's the name is a big part of this, I think.
Yeah, I mean, and so my beef with dark matter, right, as a name, is that I think it gives people really bad intuition for what it is. So when people think dark matter, they think it has a color of some kind, or that it absorbs light, because that's what we think of when we think of dark colors, right? But light just goes right through dark matter, right? So it's invisible, it's clear matter, it's transparent matter. I think my current feeling about it is that it should be called invisible matter or illuminous matter if we want to be fun. Illuminous matter is pretty good.
Trino?
Yeah. Trino. I mean, the thing about the
neutrino?
Neutrinos, we know how to catch them. It's hard and very expensive, but we know how to catch one.
Yeah.
Dark matter, we still don't have even proof of concept.
So how do we catch an axion?
Yeah, so I think that the traditional, most popular way to try and capture an axion is the one that the Axion dark matter experiment at the University of Washington is using. So this is known as ADMX, literally Axion dark matter experiment. And if a neutrino, there I go, I just said neutrino. If an axion flies through a very strong magnetic field, it will decay into 2 photons. And so you can look for a unique signature of those photons from the decay in the magnetic field. So basically, ADMX has a microwave cavity that's about this big. I like to give people a sense of scale because before I saw ADMX, the only other experiment I had ever seen was at the Large Hadron Collider. I had seen the Atlas detector.
Right.
So
That's a
I
big
went in
detector.
thinking,
Yeah.
right. And the Atlas detector is like several stories. It's like multiple opera houses, all in like space-wise, all in one place. And then I went in and they were like, yeah, this is our fancy dark matter detector. And it's like this little microwave cavity that has an 8 Tesla magnetic field inside of it. So much stronger than the Earth's magnetic field. And it's actually really hard work tuning the cavity, keeping it cold so that you don't have photons from random noise fluctuations inside the cavity. Being an experimentalist is really hard, and I'm grateful to be a theorist.
I mean, I've heard of a bunch. I know that there are experiments that have telescopes pointed at the sun, hoping to catch axions from that. I know there's some interesting like linear particle accelerators that are hoping to catch axions as they pass through matter and watch where they turn. They shouldn't pass through matter, but turn into something on the other side. And so, I mean, with that gigantic Venn diagram that you mentioned, with so many different methods of searching for dark matter, each one has tons of different experiments and people thinking of different ideas, ways to try to get to the bottom of this question. And so it must feel like you really sort of found your way into a very interesting and field with a lot of opportunities for people to come up with. Like in a lot of fields, there's not a lot of people aren't willing to entertain a lot of really crazy ideas. But I think with dark matter, they're so desperate now that and there's so many different ways that it's going right now. So do you find that there is a lot of interesting opportunity for people who want to get into this field specifically?
Yeah, so I think, the fun thing about the axion, just to go back to the 2 different problems that it solves, is even if we tomorrow find some other particle that explains the entire dark matter problem, we still do have this strong CP problem where we need to explain why the neutron doesn't actually have an electric dipole moment because we've never seen it, right? So what's interesting about the experiment you mentioned where, they're looking at the sun and trying to capture axions from the sun is that that's not actually the dark matter, the relic population that makes up the dark matter in the galaxy. Those are axions that are being produced in the sun. And that's something that might happen whether the axion is the dark matter or not. So what's fun about the axion is even if it's knocked out as a dark matter candidate, it's still interesting to think about. The axion is still a really compelling particle to go out and look for. And what would change if we found out that something else comprised all of the dark matter is that we might reconfigure which experiments we emphasize. So I think that there's definitely a long-term conversation to be had here. It is the case that when I first started working on axions, they were far less popular than they are now. And what changed is the Large Hadron Collider didn't find supersymmetry. And a bunch of people got really sad about it. I'm just gonna have to tell you, emotions are a really big thing in how theoretical physicists make decisions. We are emotional creatures. A lot of people got really sad about supersymmetry and went looking for something else to work on. And the axion was right there screaming, I'm compelling.
Right. I'm a mystery. Solve me. Yeah. I mean, like I think today, and I mean, talking to your colleagues, today's got to feel like a really important day because finally, for the first time, something unusual has happened in the field of particle physics as opposed to the Large Hadron Collider just dutifully turning up every missing puzzle piece that everyone was looking for.
Yeah, I don't know. So I actually was asking some of my good friends, if this comes up tonight, what should I say? And there were dueling messages from people. So I am generally speaking tantalized by the mu on G-2 results. I'm really interested to see what happens next. There are reasons to be skeptical. So actually the number that they measured was closer to the standard model value. At the Fermilab measurement is closer than the Brookhaven one. And the difference is that the error bars are smaller. Today, they made the argument that you can combine the data sets and then you actually get a 4.2 sigma as opposed to something in like the 3.3 to 3.7.
Yeah, that's what I'd seen.
So I think people are going to be arguing for a while about whether that combination is something that really should be done. And then there's just the uncertainty. Theorists, we know what we're doing, except when we don't know what we're doing.
Right.
So,
yeah. Well, I mean, it's always this hand in hand with the theorists and the experimenters, where you come up with an idea, the experimenters try to figure it out, or the experimenters smash things together and come to you with wreckage and going like, what's this stuff? And you guys try to figure out what's going on. I know one of the other sort of through lines with your work is sort of considering the ethical implications of the science that scientists are doing. And I know you've had a lot of thinking about nuclear weapons and how scientists were dragged into something they kind of didn't want to see built. And here we are today looking at dark matter, gravitational waves, not knowing what kinds of technology and what kinds of implications these could mean down the road. Do you think that the experience of the scientists who came before should have any guideposts for the scientists working today on even something as harmless as the humble Axion?
Yeah, I think that's a conversation that you always have to be having with yourself. I think pretty much every day. It's not necessarily about things being obvious, but about awareness and check-ins and making sure that you have the vocabulary to have a conversation with yourself about, where are my boundaries? When do I start to say, no, I can't do this? This takes things in a direction that I'm not comfortable with. And, if we look at the Manhattan Project as kind of our historical example, I think J. Robert Oppenheimer kind of got into that without really thinking about what would it really mean if we happen to be successful. And I had a conversation with Rose Frisch about this, who was an incredible scientist in her own right, but at the time of the Manhattan Project was there as one of the wives. Her husband, David Frisch, who went on to a very storied career at MIT, was one of the scientists who worked on it. And Rose told me that they hoped it wouldn't work. So there's a lesson there, which is that going in and working on something that could kill a lot of people and just crossing your fingers, hoping that it won't work, is not actually an ethical practice, right? That's not actually a rubric for should I be doing this?
It's not a plan for success or for failure.
It's not a plan for success or for failure. At some point they had to make the decision that we're going to actually make sure this doesn't work. And they didn't make that decision. Yeah. And there are, all sorts of complicated reasons why people felt like they had to do it, that people have been debating for, we're getting close to a century now of people having the conversation of what should have been done differently.
Yeah, armchair alternate history historians. Yeah.
But one of the reasons that we do that armchair alternate history kind of, experimenting with our futures, our alternate futures, right, is that we may find ourselves in that situation again. And the question is, will we be better prepared to actually think it through and proactively decide rather than being carried along by the current? And I do think that one of the things that we are failing to do in physics and astronomy is it's not built into our curriculums to help our students proactively say, yes, I am for doing this. I'm going to do it. Here are my reasons, even after I take into account the potential human impact, because we simply don't know how to make that assessment of what is the human impact. It's not part of our education to do it.
But a lot of the time, there's some real low-hanging fruit in terms of what are the environmental damage of the work that you're doing. Like a lot of stuff you can just look at and go, yeah, that's going to dump a lot of carbon dioxide into the atmosphere. So we know that we shouldn't be doing that. While other things are a lot more esoteric. You don't know that the laser is eventually going to be installed on the, 40 years from now, it's going to be put on the warship and used to,
I'll name a couple of good examples here, which is one, SpaceX has this approach to things that fail fast, fail hard, get back to it, do it all over again. The exploding rockets have an environmental impact on the ecosystems right around where they're launching, right? That has implications for birds that mate right there. So that's an example of, there's, I think, a question there, was a democratic decision made by the communities totally around there about whether that was something that they were ready to live with, the potential long-term impact that has on the ecosystem. And I think another example is what's happening in Alcantara in Brazil right now with the Black Quilombola community that are potentially going to be entirely displaced from their land because the United States and other governments want an optimal launch pad. So there's already a launch pad there. They want to expand the launch pad.
Close to the equator.
And they're basically talking about forcibly removing people from land that they have lived on for a couple hundred years at this point, simply because it's the best place to launch from. So when you're talking about that, you're talking about, these are lives, these are families, these are heritages. There are stories that are tied to the land there. So I have space telescopes that I want to see launched into space. The conversation I have to have with myself is, how badly do I want this X-ray data about neutron stars that can maybe tell me something about dark matter, versus how much do I want to support the human rights of a Black community in Brazil?
Yeah.
Right.
And I mean, I think I absolutely agree that we can, at least to have that, to stop and think about that is dramatically important. And at the same time, we also have people saying why should we be sending things to space when we should be cleaning up the Earth? But, it's like money spent in space is spent on Earth. And also, why should we have military weapons when we could be spending money exploring space? So it's also complicated. And I think the step is to just sit down and think first, and just have this conversation and have these, people who have watched the show know that I come down on every side of Starlink for the fact that it's delivering internet to remote communities here in Canada, people who've been completely cut out by the traditional internet service. And at the same time, it's ruining astronomy. So, these, and at the very least, conversations should have been had in advance to sit down and think, and how do we minimize and maximize the value for all the parties involved? Anyway, we could go on all day. You have a book.
I do.
Show us your book and tell us about it.
Can I hold it up?
Yeah, absolutely.
Yeah. So the book is called The Disordered Cosmos, A Journey into Dark Matter, Spacetime, and Dreams Deferred. It came out, what day is it? It's almost been a month. I don't even know what day it is anymore. Yeah. But it's almost been a month. So you can get it at pretty much any bookstore that sells books, which hopefully all bookstores still do at this point. Fingers crossed. Yeah. And it's a holistic look at the doing of physics, and it includes discussion about these exact kinds of questions, or like the thing I read about today, that the city of Los Angeles has spent $245 million in recent times settling like police violence cases against civilians. And I just looked at that and I was like, thinking about how much science we could have done, or as someone who was schooled entirely in Los Angeles Unified School District, what if they had just given $245 million to Los Angeles Unified School District, right? Yeah,
so that's a holistic conversation about how money gets spent, as opposed to a very specific and/or two things that have less in common than people think. Yeah. Well, congratulations. Thank you so much for taking the time to chat with us today. If you do find the Axion, will you let us know?
Yeah, I don't know. I'll think about it.
All right.
Probably want to keep that to myself.
If people want to, I know scientists won't shut up about it. If people want to find out more about what you're working on, where should they go?
Yeah, so you can find me on Instagram. Just look for my name, Chanda.Prescod.Weinstein, and you can find me as IVG Youngie on Twitter. I'm not going to spell it for you, but if you just Google my name on Twitter, you'll find it, Chanda Prescod-Weinstein.
Perfect. Well, thank you so much for taking the time to chat with us today, and good luck with your research and your writing if you ever decide to write another book.
Yeah, thank you for having me.
All right. Thanks a lot. All right, let's move on to the news portion of the week. And so let's just start with the helicopter. Carolyn, let's get into it.
Well, yeah. So Ingenuity is finally the first aircraft on Mars, right? I mean, we've had entry, descent, and landing, but that's basically from top to bottom, and nothing's taken off again. So Ingenuity's landed. It has taken its first image. It spent the night outdoors.
Now, when you say landed, you mean placed gently on the Martian regolith.
Basically, plopped itself down. Yeah.
Yeah.
The latest picture, I was looking at it today, it shows some dust on the solar panels, and I'm thinking, ooh, that's going to be kind of tough, but maybe the rotors will blow all that off when it powers up. So the first flight's supposed to happen, it was supposed to be tomorrow, but I guess they put that off till April 11th.
11th is what I've heard, yeah.
Right. Is that definite? Because everything I found said it's planned. So
they said as soon as.
Okay. So this is a little guy. It looks great in the pictures, but it really doesn't weigh all that much. It's a few kilograms. Its first flight's only going to go up a few meters off the ground. It'll be about 90 seconds of flight time. But you can think about this. It's flying through this really thin atmosphere. It's about the equivalent of 100,000 feet of altitude here on Earth, about the thickness of that atmosphere there. And there's been no helicopter that's done that here before. It has 4-foot rotors. They're going to spin at about 2,800 rotations per minute, which is about 10 times faster as any Earth chopper. I mean, I hear choppers go over my house a lot because I'm up in the mountains and I'm next to the canyon where they all fly up, and they're not going that fast. And all of that is to carry this little payload that's just roughly or maybe a little bit bigger than the size of a softball, right? So the big challenge on Mars, and I get to thinking about this, is that to have an aircraft that can fly in that thin atmosphere is a real challenge. And there's also the lower gravity, and there are other constraints on the aircraft that you have to think about. The 1% is dense. The atmosphere is about 1% the density of Earth's. So it'd be like putting an aircraft again up at about 32 kilometers, about 20 miles up.
But the gravity is the third. So you got that working in your favor.
Yeah, it's less. Yeah. So yeah. And you have to consider about, for any other aircraft, you'd have to consider things like fuel load and so on. For this one, it's got its solar panels, it's got a battery. So it's not like it has to, like have little hydrogen thrusters or anything like that. And I got to thinking about, this isn't the first time we've talked about having aircraft on Mars. During Case for Mars, way back in the day when we used to have these meetings at the University of Colorado, we would hash out these plans for these Mars missions, and we would talk about aircraft. And most of the time we talked about gliders, just because that seemed like it would be an easier thing to get to Mars. And it wasn't a new idea. I mean, von Braun talked about this in the early 60s. He talked about some kind of an aircraft that it could be used for Mars explorers. For you get down there, you build your village or whatever, and then you start going out and exploring, and an aircraft would certainly allow you to do that pretty quickly. So aircraft are still a goal, but it's got a long history. So at Case for Mars, we looked at several ideas for aircraft on Mars, basically mostly gliders, but sometimes powered airframes. And NASA has actually, not saying Case for Mars caused this, but I mean, over the years, NASA has commissioned a lot of different studies into Mars aircraft. So I got to looking at what those were. And there are a number of them, so I'm only going to talk about a few. But they had to, basically fight the challenges of the atmosphere, of the gravity. In addition to these physical conditions, you had to be able to think about something that's going to be highly reliable and usable. Because when you think about it, the nearest aircraft mechanics are going to be millions of kilometers away, and you can't really operate these things robotically from Earth. They have to be somewhat semi-autonomous. So the first one I looked at, I went back and looked sort of through the history, and one of the concepts was something called the Airplane for Mars Exploration, the AME. And it had a fairly complex wing structure that would make it very useful for these long-term, long-range flights. And the original idea was to have it fly over Gusev Crater and do some aerial studies, and then it would land on the surface. Wasn't much about how it was going to take off again, but that was about as far as they got with the planning on that. And they actually did do a drop test of a scale model for that. It was like a 20% of a regular size scale model. So they did that, and that was in 1996. And then in 98, NASA Ames developed the Mars aircraft for geophysical exploration, the MAGE, and it had a much less complex design. And their idea was that it was going to just go fly up the Valles Marineris and study that, and then it would crash into the surface. Well, we have a lot of really good experience crashing things into the surface of Mars, so we can do that. Fast forward a little bit more,
Does-
August 2001.
Doesn't feel
NASA
like a
sent-
real advantage, but sure.
Yeah, exactly. So in 2001, NASA sent another aircraft up. It was a test flight. It sent it up to 31 and a half kilometers, suspended by a balloon. And then they just dropped it and went and did a glide flight. So this sounds familiar, right? It was a proof of concept for an airframe that could function in the atmosphere. And along the way, they actually set a world altitude record with this thing. So they took the next step and they took the same airframe and they flew at a very high, thin altitude using a high-speed, very large, oversized propeller system. And unfortunately, that was sort of the end of that one because the thing broke apart during flight. But it was sort of another proof of concept. So then they sort of started looking at glider plans, and there was the ARES plane, that's short for Aerial Regional Scale Environmental Survey, and that was actually designed at NASA Langley. And it was supposed to be a rocket-powered plane that would carry an instrument load, so it would have a little bit more power, be able to carry more instruments, and that would study the atmosphere, try to do some sensitive work about the magnetic environment near the surface. It didn't get any farther than basically the drawing board and some scale model mock-ups. And then finally, there was the Daedalus concept, which was a glider that would be able to fly several hundred kilometers. It wasn't clear to me how they were going to redeploy it, but it would be deployed once, and then it would have done an exploration of this region on Mars called Coprades Cosma. So those are some of the various ones they looked at, both powered and non-powered. And the big challenges on Mars that we still have to think about, and this is kind of why we're flying Ingenuity now, is you have to get them to Mars. So we've gotten this little Ingenuity guy about this size to Mars. We got it there. They have to carry fuel if they're going to be fueled, and that's sort of a challenge right there. How much are you going to carry? Is there going to be a way when you get human crews on board to basically make new, carbon dioxide-based propellant or something like that to refly these aircraft? Once they're on the planet, you have to have these long-term sources for fuel, and you also have to be able to control them and fly them. And we don't have anybody that's flown anything on Mars. So humans out there flying around, that's going to be another challenge. But all of these concepts have led one way or another to this little rotor-driven Ingenuity craft, which is about ready to lift off the surface.
Yeah, it's interesting. I did a similar sort of run through of the literature about 4 or 5 years ago, I think, on my YouTube channel, just sort of covering every idea that's ever been presented for flying on Mars.
Well, there's a lot of them.
There's a lot. Yeah. And I ran through many of the same ones that you did. This idea of like just a long glide concept coming in on entry, a powered, even in some cases a nuclear powered airplane that would be flying around on Mars for long periods of time. But they all were very short term. There's ideas of hot air balloons that would inflate during the day and then they would deflate during the night and then sort of come back down. But
I didn't even get to the air balloon.
But none really got to the point of being as viable as Ingenuity, a tiny helicopter that takes advantage of all of this drone technology with a rechargeable battery that can just take off, fly around, land, wait till it recharges, take off again, in theory. That could serve, you can imagine future rovers being equipped with a few of these that it can deploy to use to map around its environment in a small area or send them farther afield to just make their way across the surface of Mars. It's the best idea that I think has ever been proposed, and it's on the surface of Mars right now, going to fly in 4 days. So,
and the thing, I was reading through all these, and I was thinking, 15 or 20 years ago, if somebody had said, "Oh, there's essentially going to be this drone on Mars," we didn't really think about that one when we were in Case for Mars and some of the other studies. We were focused on wings and balloons, and so this is actually pretty cool, and that's why I'm so excited about it. Is a chopper, basically a drone, is going to be the easiest thing to do. And even so, when you look at all of the work that they did to get it up there, it wasn't that easy. But now it's there and it's going to do it.
Kimberly,
Yes.
I have no question. Look
at my face.
Yeah.
So excited.
Yeah.
It's happening. It's happening soon. There's going to be a helicopter on Mars, and I am so flipping excited.
Yeah.
Can you tell with my face? Making like the really big smile with the big eyes going, ah!
I mean, obviously a helicopter on an exoplanet would be also interesting. What
Yes, but
are you
This one's
looking
happening
forward
now.
to from this flight?
I'm quite honestly, I'm looking forward more to the proof of concept. Like proving that this is a thing that we can do on a planet with an atmosphere. Like, truth be told, like the images will be cool. The fact that it's flying will be cool. It's a thing we've never done. Great. But like the proving that the technology works opens up so many doors for future missions. And I'm a little bit bummed that it's stealing the title of first powered flight on another planet from Dragonfly, but it's still really it will allow for so many new avenues of exploration. And because it is smaller, I think it can also allow for more inclusive types of science. Like, it doesn't have to be attached to this giant multi-billion-dollar rover that we have. It could be attached to a smaller mission. Like, India went to Mars for a couple $1 million, or the UAE just sent a probe to Mars. They could, in a future mission, drop a couple tiny little drones, and they're much easier and much cheaper to develop.
And
So
even you wonder
it opens
to
up
deploy.
so many more doors.
I mean, we know that with with Perseverance and Curiosity, NASA has said that this is like the biggest payload that you could feasibly land on Mars, and you had to have this really complicated sky crane and so on. With a smaller flying vehicle, you would have a much easier time. I don't think you could have it like land safely on the thin atmosphere of Mars without smashing, but still.
Maybe not, but we've gotten pretty okay at dropping things from orbit and basically having a giant parachute or a giant like bouncy ball castle, whatever.
Yeah.
To keep it from breaking. We've done that quite a lot.
But to deploy a 4 kilogram payload at the surface of Mars is vastly simpler than a
and I mean, I'm excited
two-ton.
about Ginny the same way I was excited about the Marco CubeSats that were, I think, part of the InSight mission.
Yeah.
People forget, there were 2 little CubeSats that flew past Mars attached to InSight, and InSight went down to the surface. Marco flew past, but it was the first demonstration of us sending CubeSats to another planet, and it worked, and it was great, and it's a proof of technology that can and will likely open so many more doors, not just with NASA, but with all of these other smaller space programs that are, slightly pun intended, just getting off the ground.
Yeah. I imagine sort of a future version that's just like equipped with 20 of these, and it just sort of deploys them one at a time, and they all fly off like a locust. Chris, you're a renowned helicopter skeptic. How do you feel about the mission?
Typically, I'm not a fan of helicopters, but this one I have a soft spot for.
Yeah. Yeah, I know if it's not extragalactic, you're not interested. But yeah, what are you looking forward to with this mission?
Well, I guess I learned today that this was going to be happening recently. I was vaguely familiar with the attachment to Perseverance, but I'm just excited now hearing all about this cool stuff about it. So I'm looking forward to reading about it in the future.
Yeah. That's the classic response from a galactic astronomer.
It's actually really, really refreshing because most of the people I talk to nowadays are all like, Mars, Mars, Mars. And I've sort of gotten swept up in it a little bit. So that's actually a really refreshing perspective.
Yeah, you're an exoplanetary scientist. Remember
I
that.
know.
Remember your roots.
I know.
Kimberly.
I like Venus more than Mars. I just got to remember.
Yeah, all right. Awesome. Well, it's 4 days. We're going to know. This time next week, we will know what happened. But how badly it crashed on the first flight.
Well, I think we're also familiar with the tech that's into it now because it is a drone and it has a camera that's as good as or a little better than some cell phone cameras. And it's transmitting back through Perseverance, which we're familiar with the transmission back. So this is kind of known. I mean, I don't want to say known, but pretty familiar technology. And it's all in the service of showing us what we can do on Mars.
Yeah. Yeah. Awesome. Thank you so much, Carolyn. Chris, what have you got for us? Speaking of dark matter, with the, we had a special guest. She couldn't stick around to chime in on this, but what's the discovery?
Yeah. So unfortunately, it's kind of hard following up a space helicopter. But...
Well, but it's like a dark matter sandwich. So we talked about Axions, and now we're going to talk about a different kind this time around.
Yeah, so I guess shifting gears back to dark matter. So So this is really talking about this peculiar signal that's been coming from the galactic center that we've known about for some time now. So I guess circling back, the galactic center is a very fascinating region of the galaxy for many reasons. First, it's the oldest region of the galaxy because due to the inside-out growth of the galaxy, you would expect the inner regions to be a lot older. So that's very interesting for sort of the ancient remnants of the growth of the galaxy. Also, just due to the extreme conditions in the environment, the increased density, and you can also like see the stellar orbits sort of evolving in real time. If you've ever seen like those time-lapse images of stars orbiting Sagittarius A star, it's very shocking to me as someone who's not used to seeing things happening in real time. And of course,
yeah, watching stars whip around the center of the Milky Way.
Yeah, and of course you can't forget the supermassive black hole that's there, Sagittarius A star, this 4 million solar mass like dark object looming at the center. However, there's this very puzzling mystery about the Milky Way's center that has gone unresolved, and there's this overabundance of gamma ray radiation. Gamma ray, of course, being the most energetic form of light, measured emitting from the galactic center much more than that you would predict from our theoretical models. So this access was first observed over a decade ago, back in 2009 by NASA's Fermi telescope. And so in that ensuing time, astronomers have thrown against the wall pretty much anything you can think of about that could explain this access in gamma rays. Maybe there's like this hidden population of pulsars in the bulge that could be emitting at this wavelength. Maybe something funny is happening with the supermassive black hole that could be the cause of this, or maybe something to do with the flux from neutron stars. I think Chanda mentioned that earlier.
Yeah, we had actually been reporting quite a bit that it was some kind of antimatter is being generated at the core, but that's been recently ruled out as well, I think. And colliding with matter and disgorging gamma radiation.
Yeah, exactly. In fact, that's actually important for what we're going to talk about later with the dark matter. But a great difficulty has been like, how do you properly subtract the contribution from what is known as the gamma ray background, which is just the ever-present background that you'd expect from like cosmic rays and like other known sources. And there's a lot of great uncertainty with that. And so how do you properly subtract that has been a great measure of difficulty in the modeling. But a rather exotic explanation for the galactic center access and the subject of this recent work from Mattia De Muro, a researcher from the National Institute of Nuclear Physics, is that these high energy photons that we're seeing are actually the decay products from the annihilation of dark matter. Yeah, do you have a question?
How?
That was my question too.
Yes. So dark matter annihilation. So of course, stepping back, as Chanda talked about, and what I will repeat, most of the mass of the galaxy is in the form of dark matter, and which is a phrase you've probably heard me say probably every time I've been on the show.
Yeah, we're familiar with this dilemma.
Yeah, and so this dark matter typically encapsulates the galaxy in the form of this giant spherical halo. And although dark matter is everywhere and it's all around us, the most dense regions of the dark matter halo would be at the galactic center. So density is the decreasing function of radius. And so although the dark matter is typically viewed as these slow-moving massive particles that are typically non-interacting, very rarely these particles may encounter one another, and akin to a antimatter annihilation, dark matter behaving perhaps as its own antiparticle could collide and thus annihilate, producing these high energy gamma rays. And so the conditions at the core are quite useful or quite ideal for this because of the overdensity of dark matter in the region. And so a great triumph of this recent work was testing this dark matter annihilation hypothesis. It was using the most up-to-date measurements from the galactic center, measuring the access, and perhaps most intriguingly, and why I think the dark matter hypothesis here could have some weight, is that the signature coming from the halo tends to also be spherically symmetric.
Right,
And
matching the shape of the dark matter halo as opposed to the flattened shape of the Milky Way.
Exactly, yeah.
Yeah.
So if you were expecting perhaps a more mundane explanation for the excess of gamma rays, you might expect some spatial dependence from your height from the disk, or maybe it would match onto the bulge in some way. But the fact that it seems to also be roughly spherically symmetric would indicate that the source of the gamma rays is also spherically symmetric, which you would expect if dark matter were in fact the explanation.
So does detecting the excess gamma radiation, does that help give any sense of what it is? I mean, I guess anything that is a particle that's producing gamma radiation, that narrows the list tremendously, right?
Yes, in fact, I think if we want to continue down this track of dark matter being the possible explanation, one thing that I'm very curious about, and something I'm hoping to read about, is if this is in fact due to dark matter annihilation at the core, you should also expect this from other cores. So there should be an access.
Oh, interesting. Okay, yeah.
There should be an access in gamma ray radiation coming from the core of the Large Magellanic Cloud, for instance,
Or Andromeda, yeah, yeah.
or Andromeda, or any other of these. The nearby systems would probably be the easiest to measure.
Right.
And so one thing for me is definitely looking at how well are the constraints from the gamma ray observations of external systems, and what can that tell us about what we're seeing here in the Milky Way too.
But gamma radiation is a tricky thing to detect because it's blocked by the Earth's atmosphere. So you need a satellite to do this.
Oh, of course.
Yeah. And I know you can't just build a lens and image gamma radiation. You've got to have just this really complicated instrument that does scintillation and is redirecting gamma rays down this pipeline. It's tricky business to detect gamma radiation, so it requires a very specialized tool. But still, I mean, fascinating possibility.
Yeah, and the dark matter decay products may not always be gamma rays. There's some very exotic models where the dark matter may annihilate and form electron-positron pairs or something like that. There's a lot of intriguing, there's a lot of intersection here between the particle physics and also galaxy astronomers like myself.
I do love that it's kind of a race between the particle physicists and the astronomers. Both are, have serious ways that they can search to explain the nature of dark matter. It could come from either direction. The largest scale or the smallest scale could solve this problem. Anytime soon. Thanks, Chris. That's awesome. All right, last but not least, Kimberly, what have you got for us?
I have another very, very cool mission. Not as cool as a helicopter, sorry. Well, it's very hard to come 2 stories after a helicopter still. But NASA, having just wrapped up at asteroid Bennu with OSIRIS-REx, is already prepping and has been prepping for its next asteroid mission called Lucy, which is a very, very cool mission. We've gotten sort of used to a single spacecraft visiting a single asteroid and studying the heck out of it for a while and then coming back. We've sort of gotten used to this very highly detailed in-depth studies of single asteroids and then using those to better understand the other asteroids that they resemble. Lucy is going to do that times 7. It is visiting 7 asteroids in a single mission over a span of almost 2 decades. It's going to visit 6 Trojan asteroids. So those are the asteroids that both lead and follow Jupiter in its orbit at its L4 and L5 Lagrange points, those stable gravitational points. There are clusters of asteroids before and after Jupiter. It's visiting 6 of those and also visiting at least 1 asteroid in the main asteroid belt between Mars and Jupiter, mostly because it needs to swing around the sun a couple times, swing around the asteroid belt a couple times in order to get to both sides of Jupiter. But it's still a very interesting mission going to study a wide range of asteroids that likely formed all throughout the history of the solar system, as opposed to, one asteroid formed at this particular point, and then having to have multiple missions to piece together the timeline of the solar system. Lucy will be able to sample asteroids that were formed throughout the solar system's history. And just recently, NASA announced that Lucy completed one of its very critical testing stages, which is the full deployment of its solar panel system. This is a massive solar panel system that Lucy has. And this is something we touched on briefly when the Juno mission was getting launched, is that Juno, being at Jupiter so far away from the sun, had to have the biggest solar panels ever because it's so far away from the sun.
Yeah, you get 1/25th the energy out of Jupiter.
Right. And Lucy is going even farther than Juno will be going from the sun. Its solar panel array can cover something like a 5-story building. It's, when one of the solar panel arrays is fully deployed, it's like 7 meters across, 24 feet across. It's huge. It's so big it cannot actually support its weight in Earth gravity when fully deployed. That was a very tricky thing that they had to figure out when they were testing it. But the solar panels are necessary. It's fully solar powered, though it only needs like 500 watts of power to do its thing. It needs quite a bit of solar panel area to do that. And so getting the solar panel array to fully deploy perfectly the first time is basically the most important component of this mission. And I think the scientists, they compared like the 20-minute duration that it takes to fully deploy the solar panels, 20 minutes to fully deploy this array. They equated that to the 7 minutes of terror from a Mars landing.
Right.
Because if this bit doesn't work, the entire 12 years it'll take to get out to Jupiter are for nothing. And the however many years it's going to spend out there are going to be, you can't even do that.
It's
so
I mean, it's similar to the whole
minutes.
James Webb situation,
Yeah.
all of the unfurling and actuating that needs to happen to be able to deploy the sun shield and the actual mirrors itself.
But so far the news is good. Lucy underwent this solar panel deployment test around the new year, and they've been analyzing all of the results from that, being very careful, folding it back up again very carefully. And it passed the tests with flying colors once they were able to, they had to counterbalance the weight of the solar panels in Earth gravity because they're so freaking big. They would fall over and collapse on themselves. But they fully deployed it. It worked perfectly. It worked exactly as expected. They folded it back up. I don't think they're going to unfold it again before the launch, which is in the middle of October of this year. It's only a couple months away.
I can't believe it.
Yep.
I wonder if anything else important is going to be flying in October. Anyway.
There's another asteroid mission that's launching in December.
I feel like there's something bigger.
Psyche.
Something James Webby flying in October. Awesome. Well, I'm
anyway, Lucy is making some strides towards launch, which is really great to hear. And we're not using the James Webb word.
Yeah.
And the launch word in the same sentence.
We can't
and
jinx
jinxing
it.
anything.
Yeah, like what are you gonna do? Jinx it more? Come on. It's reached maximum jinx.
There is no maximum jinx with this one.
Really? Oh, okay. All right. No.
Yeah.
All right. I thought there would be, but okay. Fine.
Sky's the limit with that one.
All right. Well, I'm excited. I did a video on that. The obligatory factoid that I like to tell people is there's as much stuff in the Trojan field, Jupiter Trojan field, as there is in the asteroid belt. Like it's the solar system's second asteroid belt that you didn't even know about. You're on my screen, Kimberly.
Hi.
Tell us what you're working on and where people can find out more.
Ooh, right now, actually earlier today, I had a fascinating interview with a group of scientists and educators who are developing programs and applications and citizen science projects to allow people who are blind and low vision to experience a solar eclipse. And it was really, really fascinating to talk with them. This technology that they developed in time for the 2017 eclipse and are updating for the 2023 annular eclipse and the 2024 total eclipse. And it was just really fascinating to learn about this technology that they put together. So that's what I'm working on right now.
I've seen this with other things, like being able to see galaxies and being able to see planetary surfaces and things like that. But an eclipse.
An eclipse, which is traditionally thought as such a very highly visual experience.
Yeah.
And therefore is inaccessible to people who cannot use that sense. It's wonderful technology, wonderful applications they've put together. So that's what I've been working on, and it's really fascinating.
And if people want to follow your work, where should they go?
Oh, right. Obviously, I should talk about that. They can follow me on Twitter at AstroKimCartier, and always I write for eos.org.
Perfect. Chris, what are you working on?
I'm actually inching closer to the publication of my first author paper. So
that's awesome. What do you have a working title yet? Oh, you don't want to spoiler it yet.
I have no working title yet. We're probably having something to do with the Milky Way smashing together with Sagittarius and the remnants of that, something like that.
All right. Well, my job all day long is to come up with titles for my writing team. So let me know. We can workshop something. If people want to follow what you're working on, where should they go?
You can follow me on Twitter at @TheRealCCar. I tweet stuff. So.
Awesome. Carolyn, what are you working on, and what can people find out more?
Yeah, so I got interested enough in the Mars aircraft thing that I'm actually working on 2 or 3 more articles. The next one's going to be about balloons. Since you mentioned those earlier, I was going to say I'm working on the next one about balloons because they're not a dead technology yet. So they could very well be used again in the future on Mars. So I'm going to explore that.
Yep, there's lots of great old NASA proposals about that, for sure.
You can. It's a rat hole.
It really is.
It's a rabbit hole. It really is.
Well, I mean, just all those old NASA papers are rabbit holes. Like, I don't think people understand how many of the ideas that we're even seeing today were thought of back over the last 50 years by NASA. You can go back and I always say you can see the SpaceX Starship in versions of NASA proposals for what the space shuttle was going to become, a fully reusable 2-stage rocket system. NASA had this plan in the 1960s, 1970s.
Absolutely.
So there's so much history there. That's
a treasury.
Amazing.
It really is. So.
Yeah, until they learned how hard all this stuff was, got a lot more conservative. And if people want to watch what you're doing, where should they go?
thespacewriter.com is my website, and I'm on Twitter at @thespacewriter.
Awesome. All right. Well, and for me, I just posted a whole bunch of upcoming interviews. I just had an interview with Dr. James Davenport, who is he's a YouTuber, but he's also a scientist, researcher, works out at the University of Washington. We had a great conversation. I think you'll really enjoy it. And then tomorrow, I've got the conversation with Avi Loeb. Next week, Dr. Paul Sutter is going to come back and explain the muon G-2 experiment. So we're going to spend like an hour and just go over it, because you might think he's just a grumpy astrophysicist, but he's actually a particle physicist, and so this is his specialty. So we'll talk about that. And then I've got an interview with Dr. Michio Kaku after that, as well as a bunch more. So I've been sort of working hard to organize a whole bunch of interviews. Who else? Jesse Christensen's coming back. Tons and tons of really interesting people. So hopefully you'll come back to my YouTube channel and follow some of that. I'm going to put you guys all back on the screen. There you all are. Okay. Well, thank you, everybody, for joining us today on the Weekly Space Hangout. We really appreciate it. Thanks to all of the moderators. Thanks to people who are showing this both on YouTube and on Twitch. Thanks to all my co-hosts, our special guest. A special thanks, as always, to Nancy Graziano for all of her help. And we will see all of you next week in some variation. Thanks, everyone. All right. And the classic question, where is the stop button? All right.